This conference will now
We
be
understood
recorded.
what exactly is communication, what are the different types of communication, different modes of communication, and why exactly is a protocol required. So we got to know the answers for these four questions. Then after that, we started with the very first communication protocol, which is nothing but UART. And UART stands for Universal Asynchronous Receiver and Transmitter. So when it comes to the UART protocol, looking at the features of this protocol, we understood it's an asynchronous protocol first, and it is going to give us any duplexity. You either can achieve half duplexity or you can achieve full duplexity. But generally, people prefer achieving full duplexity when there is an option provided. And the devices in this protocol are generally not referred as master and slave. They are referred as host and the devices. Whoever is transmitting will be considered as host. The one who is receiving will be considered as the device. Then the two lines which are used for the interfacing is transmitter and the receiver. So if it is receiver in one device, it will be a transmitter on the other device. If it is a transmitter on one device, it will be a receiver on the other device. So we saw the hardware configuration. So between the two devices, if the device one is transmitting, device two is receiving, and device two is transmitting, device one is receiving. You have to observe the direction of the arrows as well. Then we saw the frame format of how exactly the data gets transmitted at the end. So when the data transmission is happening, first we are going to transmit a start bit. Then after a start bit, we are going to transmit 8 data bits. Start bits are generally 0. Then 8 data bits will be varying from D0 to D7. Then after the 8 data bits, we are going to transmit one parity bit. A parity bit will either be a odd parity or a even parity. So if the data has odd number of ones, you will have odd parity representing a 1. So if the data has even number of ones, it represents even parity, and parity bit will have a 0 return. Then after the parity bit, we are going to transmit a stop bit. So we have two stop bits, that is two ones. So we understood this, how frame format gets transmitted. Then after this, we were discussing things with respect to the baud rate. Baud rate is always referred as number of symbols being transmitted per second. A symbol can be made up of a single bit, or it can be made up of multiple bits when you are using any of a modulation technique. So sometimes you can call the bit baud rate as bit rate as well, which represents number of bits per second. Now the frequency of the data transfer is in fact nothing but the baud rate, and it is always suggested that both the transmitter and the receiver are going to agree upon communicating with the same common baud rate. Now it is very important that both the transmitter and receiver are agreeing to work with the same baud rate. Now here is an example which shows what happens if the two devices are not working with the same baud rate. What if the two are working with two different baud rates? Now assume the frequency at which device 1 is working is let's say 2 hertz. Okay, so the frequency at which device 1 is working is 2 hertz. Assume it is faster. And the frequency at which device 2 is working is 1 hertz, comparatively slower. Now, if the frequency is 2 hertz, that means you are going to transmit 2 bits per second. In 1 second, you are going to transmit 2 bits. And in case of frequency being 1 hertz, you can transmit or receive 1 bit per second. Okay, so in 1 second, you can either transmit or receive 2 bits in case of device 1 because it is working with 2 hertz of frequency. And in case of device 2, so any device working with 1 hertz can receive 1 byte of data at a time. Sorry, 1 bit of data at a time, or transmit 1 bit at a time. Now assume device 1 is, as I said, comparatively faster. It is working with 2 hertz. Assume the data transmission starts. Device 1 is transmitting. So device 1 is the transmitter here. and device 2 is the receiver. So device 2 has to just receive the data. So device 1 is transmitter and device 2 is receiver. Now if device 1 first starts transmitting and it has to first transmit a start bit. So how many seconds do you think device 1 will take to transmit a start bit? How many seconds device 1 will take to transmit a start bit? I'm saying 2 bits per second gets transmitted. Yes. So it will take only 0.5 milliseconds. I mean 0.5 seconds if I'm speaking with respect to the seconds. So it is taking 0.5 seconds to transmit one bit. So in the first 0.5 seconds, device 1 is going to transmit the start bit. Now device 2 is going to receive it. Now how much time do you think device 2 will require? Okay. So how much time do you think device 2 is requiring? Yes. So device 2 is requiring 1 second. Okay. So device 2 is requiring 1 second. So remember device 1 is transmitting 1 bit in just 0.5 seconds. But device 2 is consuming 1 whole second to receive the start bit. Now by the time device 2 is done receiving a start bit, device 1 has also transmitted the first data bit. In the first minute, in the first second, device 1 transmitted a start bit, it also transmitted a D0 bit. But in case of device 2, it has just received only a start bit for the complete 1 second. Now in the second, okay, so device 2 is actually transmitting data 1 bit. So whatever data 0 bit it transmitted, it is lost. Device 2 was not able to receive it. So that data is lost. So now device 1 at the second, it is transmitting D1, data 1 bit. Now device 2 receives that D1 bit, but it assumes as if it is the first data bit. So in the second, this is the first data it is receiving. So it assumes to be it is the first data bit. Then D2 will also be lost. So device 1 will obviously transmit, but device 2 will not be able to receive it. In the third second, device 1 transmits D3 bit, but device 2 receives it as a D1 bit. So data 1 bit. It is going to receive it as a data 1 bit. So this way, if you continue, at some point of time, device 1 is actually transmitting a stop bit, but device 2 is still understanding it as a D4 bit. It is still understanding or interpreting it as a D4 bit. Now, do you think device 2 was able to receive the data whatever device 1 transmitted properly? Did device 2 receive the data properly? No. So device 2, because the device 2 was working with lower frequency, device 1 was working with higher frequency, device 1 kept transmitting the data. Device 2 was obviously receiving, but it couldn't receive 2 bits of data at a time. So its frequency was 1 hertz only. It could receive only let's say, bit of data in 1 second. So for every alternative bit D2 was receiving, the device 2 was receiving. So it has lost one more bit, whatever device 1 has transmitted. So this way, it was always a problem. It is always a problem, in fact, if the two devices are not agreeing to work with the same frequency. So it is very important that the two devices will agree to work with the same baud rate whenever data transmission or reception is happening between the two devices. It is not just in the UART protocol, it is in any given protocol. So any given protocol you take, it is necessary that you make sure the two devices are always working with the same baud rate. Else, whatever data gets transmitted will not be properly received by the receiver. Understood why baud rate is important? Okay. So the next slide, we spoke about that yesterday already. So first, it's only in asynchronous, right? For synchronous, we have clock. Yes. So for synchronous, you obviously have clock. So depending on the clock signal, you transmit the data. And in case of the synchronous, or like in the synchronous communication, so you may transmit the data, you may receive the data. So master will generate the clock pulse and accordingly transmission and reception happens. Okay. So there the clock frequency is important. So you have to look in what clock frequency the device can communicate. Accordingly, you have to set the clock frequency. Okay. Fine. So whenever the communication is happening, you have to make sure the two devices are agreeing to work with the same baud rate. Now, this slide was actually talking about the relationship between the baud rate and the bit rate, which we have discussed already. So bit rate is nothing but n multiplied by the baud rate, and n represents number of bits in each symbol. So after this, the next we have got is to implement. Theoretically, it is this much only when it comes to the UART protocol. So first thing you have to remember is the feature of UART. It's an asynchronous any duplex communication protocol. How configuration happens, how frame gets transmitted at the end. Now let us try implementing a project on this with the help of a UART protocol. Now, can you tell me whether UART is an inter-board protocol or an intra-board protocol? What type of protocol it is? It's an inter-board protocol. So communication is happening between two chips of what? The communication is happening between two chips of, yes, two different boards, not same boards. Communication is happening between two chips of two different boards. Now, we will take two boards in our example. Okay, so the first board we are going to deal with is your laptop. Okay, so whatever motherboard your laptop has, that's the first board we are dealing with. And the second board we are going to deal is your PixSim board. Okay, so we are going to establish the communication between the laptop and the PixSim board. Now you might be thinking we already are using the PixSim board on our laptop, and do you think the UART is already running in the background? No, that is not happening. So you are running PixSim as a software on your laptop, but there is no connection between your processor on the laptop with the PixSim board's microcontroller. So whatever you did so far was you were writing your code on the laptop and you were dumping that code into the microcontroller, and microcontroller was executing that code. So there was no communication happening. So you were just using the laptop to have the program returned to get an executable file generated, and that executable file was returned on the microcontroller which is available on the PixSim. So there was no communication happening so far. Now we are going to establish a communication. Okay, so we are going to establish a communication. If we connect the PixSim board externally via USB port, it will. No, like even in that case, yes, when you are establishing a connection, you have to make sure communication is happening with the UART block. So just if you connect, it's for example, assume you have a file on your laptop, okay, and you are copying that file to your mobile. You are connecting the mobile to your laptop. You have a file written on your laptop and you are copying it into your mobile phone. That's it. So there is no communication happening between the two devices. So your laptop was just having the file inside it. Sorry, your mobile now will have a file, and going ahead, you will just use the file from your mobile. There was no communication happening. So to establish the communication, you have to use a protocol, and we are going to make use of UART protocol now. So we are going to establish the communication between the laptop and the PixSim board. So now whenever I have to transmit, whoever has to transmit will be the host, the one who is receiving will be the device. As we need keep common ground between the two different boards should be near to each other, then only UART will work so far. Long distance between the boards, UART won't work, right? Yes. So that is to have the communication established. It's a wired connection. So obviously you have to make sure there is a close contact between the two devices, as close as possible. You cannot keep it for a very long distance and make use of the hardware connection. So it's a wired communication. You have to establish the connection between the two. Okay. Now, if you observe laptop and PixSim board as two different boards. So laptop's motherboard is one board, PixSim is another board. Okay. Now, physically, if you feel there is a PixSim board, between the laptop and the PixSim board, you will connect the wires, right? So between the laptop and the PixSim so you are going to connect the wires. But now we don't have PixSim as a physical board. What we have is a software. It's a simulator. PixSim is a simulating software that is also installed on our laptop. Now, in order to have the connection established between the two, like wires, in case of a software, we have something called as null modem emulator. Did you do the installation of this null modem emulator? Did you do the installation of null modem emulator in today's lab? The serial port? Not yet? Okay. So you will be instructed to Teratum and serial port. Yes, that is what I'm saying. So did you not see null modem there? Null modem emulator. So you must have did it. Okay. To establish the communication between the two, you need this null modem emulator. Fine. Now this is like a bridge. It is like a cable which is connecting your laptop and the PixSim board. So as of now, we don't have a physical PixSim board. So we are using a software version of it. So we are going to establish the communication between the two. Now we have to do the serial communication between the laptop and the PixSim board. So the PIC microcontroller has a built-in UART block. So PixSim board has a PIC microcontroller. So PIC 16 F877A. Okay, and this comes with a built-in UART block. Okay, the PIC microcontroller comes with a built-in UART block, and we are going to make use of that built-in UART block to have the serial communication done. On the laptop, for the serial communication to happen, we need a software called QtCom. So QtCom is a serial terminal. It's an application which helps you transmit or receive the data bit by bit. So generally in your processor, the CPU's processor, so there is parallel communication happening. To establish the serial communication between the laptop and the PixSim board, you are going to make use of QtCom. Okay, so what you have to understand is we are now trying to establish the communication between your laptop and your board, the PixSim board, which has a PIC microcontroller inside it. So now we have to establish the communication between the two. Now device 1 is the host because that is the one which is going to transmit, and device 2 will be the device, just the device. We call it as device. Now what we are supposed to do is from my laptop, assume I'm going to transmit character A. Okay, so from my laptop I'm going to transmit character A. That character A has to be received by the microcontroller which is on your PixSim board. So receiver has to receive that character A. Now after that, your receiver, whatever is available on the PIC microcontroller, should receive the data. Then the same data has to be transmitted back to the QtCom, and QtCom should receive that. So character A should be received here. So this is what we have to be achieving. From the laptop, you have to transmit character A. Then your receiver has to receive that character A. Okay, so your PIC microcontroller should receive that character A. Then that character A has to be transmitted back by the PIC microcontroller which has to be received by the QtCom. Now, if I have to show you that, so this is QtCom. I will open that and let me also open the Fixing Lab. Okay. Now, these two you can assume as two different boards. Okay. On the left hand side, you have QtCom. On the right hand side, you have the PIC microcontroller board, which has the PIC microcontroller. Okay. Now, what you are supposed to do is you have to establish the connection between the two, and that is done with the help of null modem emulator. So, you are going to establish the connection. Now, whatever I transmit from my QtCom here, that has to be received by your microcontroller here. And whatever microcontroller receives, that has to be transmitted back to the QtCom. So like this, we are going to establish the communication. So you transmit something, your microcontroller has to receive, your microcontroller receives something, the same will be transmitted, which will be received by the QtCom. Understood the requirement of the project? Okay. Now let us start with the coding part. We already have template for that. So let me directly open the template without wasting time. So here I'm going to open the project, and the name of the project is under UART sources. We have something called as the driver. Oh shit, it's not this. I'm sorry. So I'm going to open driver polling. Okay. Now, first and the foremost thing, start. Okay. So we have some header files. We have some source files. I'm opening the source file main.c. So I have taken some LEDs initialization initially, and I'm going to call init UART function by passing 9600 as an argument. So 9600 is the baud rate at which we are fixing to establish the communication. Both the laptop and the microcontroller are going to work with the same baud rate of 9600. So we have to do the initialization of the UART block and set the baud rate to be 9600. Now the initializing function is written in a separate .c file. Yes, 9600 bits per second. That's the 9600 is the frequency. Yes, that means 9600 bits per second. Now coming to the initialization. So we are going to make use of the built-in UART block of our microcontroller. Now how to get the built-in, how to know the features of the built-in UART block of our microcontroller? What should we be referring for that? Yes, we have to refer the data sheet. Okay, so let me open the data sheet of the microcontroller, and here I'm taking you to the table of contents. You can look at this and decide which section to be referred for UART block. Can you tell me which section to refer? Yes, it is section number 10, which is addressable universal asynchronous synchronous receiver and transmitter. Now, the universal synchronous asynchronous receiver and transmitter is one of the two serial input output modules. Okay. Now, the UART can either be configured in asynchronous mode or synchronous mode. Now, if it is in asynchronous mode, you can achieve full duplexity, and if you are in synchronous mode, you can only achieve half duplexity, but you can either configure it as a master or you can configure it as a slave. So the disadvantage of synchronous mode is you can configure it only in a half duplex mode. Now, let us not focus on synchronous and let us look at the asynchronous way of data transmission and reception, because I want to achieve full duplexity. Okay, so here what it says is, in the UART block, configuration as a full duplex asynchronous system is used to communicate with the peripheral devices. Okay, it can be with any of the peripheral devices. Next, bit SPEN, which is the seventh bit of the RCSTA, and bits TRISC 7 and 6 have to be set in order to configure the pins R6 and R7. So it is telling I have to configure SPEN bit, which is the seventh bit of the RCSTA register. Also, I have to configure the seventh and sixth bit of the TRISC register. It has to be set. Set means what should I write? What should it be written? Yes, it has to be written with 1 in order to configure RC6 and RC7 as universal synchronous asynchronous receiver transmitter. Now, RC6 is the pin where the transmitter of the UART block is available, and RC7 is the pin where the receiving of the UART block is available. So RC7 is the receiver. I will make a note here. RC7 is the receiver. This is this is RC7 pin of the microcontroller, and transmitter is available from RC6 pin. And from pin configuration, please go slow and revise one. Okay, so I'm repeating this again. Okay, coming to the data sheet back. So in case of UART block, in case of configuring it in an asynchronous mode, it says something like this. The bit SPEN is the name of the bit, which is the seventh bit of the RCSTA register. It's the seventh bit of the RCSTA register. Now, the SPN bit and bits TRISC 7th and 6th have to be set. Set means it has to be written with the value 1 in order to configure the pins RC6 and RC7. RC6 is used for the sake of transmission. RC7 is used for the sake of reception. Okay. Now, when it comes to the asynchronous mode, okay, I have the list of registers to be used. Let me first show you the list of registers associated to the UART block. I'm just scrolling down to show you the list of the registers. You can see registers associated with the asynchronous data transmission. Now I have one intcon register where I'm using only 2 bits. I have PIR1 register. I'm using only 1 bit in that register. Then RCSTA register, which I'm using only SPEN. Then TXREG, that is the transmit register. PIE is the peripheral interrupt enable. I am using TXIF pin only. Then TXSTA transmitting status register, and SPBRG, it is the baud rate generating register. So these are the registers associated with the asynchronous data transmission. This is for the transmission. And in case of asynchronous mode, we don't just transmit, we are also going to receive. So these are the list of the registers which are used in the reception. So intcon register, PIR register, RCSTA register, RCREG register, PIE register, TXSTA register, and SPBRG register. Okay. Now we have to start with the configuration of the bits. So I'm going to start with the registers configuration. So first register we are going to configure is TXSTA register. Okay. So Okay. So let us start the configuration of TXSTA register. It's the transmit, status and control register. TXSTA is the transmit, status and control register. Now, this TXSTA register has 8 bits and one of the bit is an unimplemented bit. Okay. Rest of all other bits, rest of the 7 bits, out of the remaining 7 bits, 6 bits are readable as well as writable and 1 bit is only a read-only bit. Okay. Now, starting with this, let me start with the configuration from the very first bit, that is CSRC. Now, CSRC represents clock source select bit, and in case of asynchronous mode, it's a don't care bit. So you don't have to be worrying about the CSRC bit, it's a don't care bit. Then we have TX9 bit. Okay. First of all, I have to first decide how many bits of data I have got to transmit. So whether I have 9 bits of data to be transmitted or I have 8 bits of data to be transmitted. Now, depending on that, you can set whether you are going to transmit 8 bits or 9 bits. And in our case, I'm going to transmit 8 bits only. I don't have 9 bits of data to be transmitted. Now, if I have to transmit 8 bits of data, what should TX9 be returned with? Yes, so I should have it returned with the value 0. By default, it is already 0. Hence, I'm not going to change that bit. Okay, so I want to transmit 8 bits of data if I am transmitting. So I have to write TX9 with the value 0. R/W, sorry, the TX9 is already 0. So I don't have to change it. Next, it is TXEN, which stands for transmit enable bit, whether you have to enable the transmission or not. Now, do you want to enable it or not? I have to enable it. So to have the transmission enabled, what should I have TXEN return with? Yes, I have to write it with 1. Initially, it is written with the value 0. Because I have to write it with 1, I'm having it return here, TXEN return with the value 1. Okay, so that is TXEN, transmitting enable bit. Then after that, we have bit number 4, which is SYNC, which is used to select whether UART is in asynchronous mode or it is in the synchronous mode. So you have to select the mode with the help of SYNC. So what should I have SYNC returned right now in our case? Yes, we are going to configure it in the asynchronous mode. So SYNC has to be returned with the value 0. So anyways, it is returned with the value 0. I'm not going to rewrite it again. Then bit number 3 is an unimplemented bit. So we don't have to be worrying about it. Then we have to go with BRGH, whether you want to select the high baud rate or you want to make use of low baud rate speeds. So we have certain speeds which come under high speed. Some of the frequency come under low speed. So whether you want to choose the high speed baud rate or the low speed baud rate, you have to decide here. Now I want 9600 and I will show you a table where the frequency is going to belong. You can see here. So this is when BRGH is returned with the value 0. Okay. So it is BRGH returned with the value 0. So you can see for 9600 baud rate. Okay. So we have to write certain value here. Now the problem with this is, okay, here the baud rate, whatever you are going to use, is going to like reduce. Okay, comparatively, when you say 9600, you don't achieve exact 9600 in case of low speed. So you always have to make sure you are working with a high speed baud rate. And in order to achieve the high speed baud rate, so I have to represent the microcontroller that I want to work with a high speed baud rate. So what should BRGH be returned with? Yes. So to have the high speed selected, BRGH has to be returned with the value 1. Now the default value of BRGH is 0 and I'm going to have it returned with 1. You didn't get? Okay, let me repeat this again. So when it comes to the baud rate, okay, so you can select whether you want a high speed baud rate or a low speed baud rate. Now, if you see, when it comes to the low speed baud rate, and you are going to specify 9600 as the baud rate, you will not achieve the exact 9600. You can observe the percentage of error here. So, percentage of error is approximately 1.73. But in case of high speed baud rate, okay, when 9600 baud rate is selected, the percentage of error is comparatively less. So generally, when you want to establish a communication, it is preferred to go with a high speed baud rate compared to that of a low speed baud rate. You may not achieve the exact low speed baud rate you are specifying. So I have to write high speed baud rate. Hence, I am going to write BRGH with the value 1. That is written in the code also, BRGH written with the value 1. Okay. Next, the next one is a read only bit. Okay, the next bit here is a read only bit, TRMT. Now TRMT is a read only bit which is transmit shift register status bit. That is the status bit of the transmit shift register. Now, in this case, TRMT will be either 1 or 0. It's a read only bit. You are not supposed to write into that bit. It's a read only bit. Now, if TRMT is returned with the value 1, then TSR register is empty. TRMT returned with the value 0, then TSR register is full. Now, before I speak about this TRMT and TSR register, first you have to understand how you are going to do the transmission of the data. So how the data transmission happens. So I'm scrolling down and taking you to the data transmission. You can see UART asynchronous transmitter. How is it going to work? Now coming to the UART transmitter block. Whenever you have to transmit with the help of a UART block, what happens? First, the heart of the transmitter is the transmit shift register. The shift register, it is the TSR. The shift register obtains its data from the read or write transmit buffer register. Then TXRE, it is the buffer register TXREG. The TXREG register is loaded with the data in the software. The TSR is not loaded until the stop bit has been transmitted from the previous load. So whenever you have to transmit some data with the help of the built-in UART block, you are going to make use of some special registers. One is TXREG, the other one is TSR. So first, whenever you have to transmit the data, assume in this case I have character A to be transmitted. Now, whatever data I want to be transmitting, so it has to go to the QtCom, that is your laptop, with the help of a transmitter, which is available in the UART block. So, anything you want to transmit that cannot be directly returned to the transmitting pin directly. So instead, any data you have got should first be returned to the buffer register, that is TXREG register. So any data you have got to be transmitting should be first returned to the buffer register, TXREG. Now from the buffer register, please understand any data you are going to transmit will not get transmitted directly. Any data you are supposed to transmit will be first returned to the TXREG register called as the buffer register. Now once you are done writing the data, this data gets returned to the TSR register if it is empty. So TSR means transmit shift register. So it gets returned to the transmit shift register. Any data you want to transmit, after you writing it into the TXREG register, it then gets returned into the TSR register. From the TSR register, data gets transmitted bit by bit. First, a start bit gets transmitted, then 8 data bits get transmitted, one parity bit gets transmitted, and 2 stop bits get transmitted. So that way, data will be transmitted with the help of the transmitting pin on your UART block. So any data you are going to transmit should be done like this. Okay, you can pictorially see it like this. Whatever data you have got, you first write it into the buffer register. This is the data. Whatever data you want, you write it into the buffer register. From the buffer register, it gets returned to the shift register. So what shift register does is, it is going to transmit the data. First it transmits a start bit, then it transmits 8 data bits, then it transmits a parity bit, stop bit via the RC6 pin of your microcontroller. So like this, via the RC6 pin of your microcontroller. This is how transmission is going to happen. Now, whatever data you have written into the TX-REG register can be returned to the TSR register only if it is empty, correct? So any data you write into the TX-REG register should be returned to the TSR register only if it is empty. So I have to check before I have the data to be returned. I have to check the status of this TSR register, whether it is full or it is empty. And that can be done with the help of this read only bit, which is nothing but the TR empty bit. So whether TSR is full or TSR is empty, I can decide with the help of TR empty bit. Now, depending on the status of this, I'm going to have my data returned to the buffer register. The data waits in TX-REG to be loaded in the TSR. Yes, data is going to wait, but how long? So rather than you just write the data and leave it off to wait, it is good to write the data after confirming whether the transmitting bit, whether the TSR is empty or not. So that we are going to decide with the help of TR-empty register. Then TX90 is the next bit. After TSR, start bit added or at the start only. So once you have the data returned to the TSR register, it automatically starts transmitting the start bit by itself. It first transmits a start bit. See, TSR is also a register of 8 bits only. Okay, so while the data is being transmitted, it automatically first transmits a start bit, then 8 data bits. Then after the data is transmitted, it calculates the parity, transmits the parity, and then it is going to transmit a stop bit. Okay. Now, by chance, if you have 9 data bits to be transmitted, that 9th data bit, whatever you want to transmit, has to be returned here in the TX90 bit. Whatever 9th data bit you have got to transmit should be returned here in the TX90 bit. So if you have TX90 bit, return with any data you want to transmit. So it is going to transmit the 9th data bit, else it is going to have the parity bit written. So this is about the transmitting status and control register. Clear with this? Okay. Now, not just this, we also have to receive the data. So we have to also configure the receive status and control bit. If 9th bit data, then wait. Yes, as I said, if 9th bit is data, you are going to compromise with the parity bit. So you cannot transmit a parity bit. If the 9th bit is a data, you are going to transmit the data bit only. Parity bit cannot be transmitted. Then you are going to make the compromising on the parity bit. So it's like you are saying you're okay to compromise with the parity bit, but you want to transmit 9 data bits, then you have to transmit that 9th data bit in the parity place. Okay. Then after transmitting, we have to configure the receiving also. Okay. So reception also has to be transmitted, has to be configured. So to start with, The name of the register is RCSTA. It's the Receive Status and Control Register. And this is going to have 8 bits, bit number 7 to bit number 0. Now, all like the first 5 bits are readable as well as writable, and by default, it has the value 0. The last 3 bits are read only bits, where 2 bits are having the value 0 returned by default, and one has a don't care bit return. Now, first we have is the SPEN. Okay, so SPEN is the bit which is used to enable the serial port. So whether we have to enable the serial port or not, we have to write it with SPEN bit. So if SPN is returned with 1, we are going to enable the serial port, that is RC7 and RC6 will be configured as receiver and transmitters. Else, if you have SPN returned with the value 0, I'm going to disable the serial port. So what should I write to SPN right now? Yes, so SPN has to be returned with the value 1. So that is the next thing we have to return. SPEN is returned with the value 1. Then it is RX9 bit. Okay, so this is RX9 bit, which is used to do the receiver settings. Whenever we are going to receive the data, okay, so we have to tell whether I have to receive 9 bits or I have to receive 8 bits. Okay, so we have to decide whether we receive 8 bits or we receive 9 bits. So as of now, if I'm transmitting 8 bits, then obviously I will receive 8 bits only. But it completely depends on the host. Yes, it depends on the host system, how many bits you are going to transmit. 99% of the times, generally it will be 8 bits itself. It's a very rare scenario that it is 9 bits. So if it is 9 bits, you have to communicate with the host first. You have to make a decision to receive 9 bits earlier itself. Now, because I'm transmitting 8 bits, I'm assuming I will also receive 8 bits only. So I have to write RX9 with the value 0. Okay. So initially RX9 anyways is returned with the value 0. So I'm not going to change it again. Then SREN is the single receive enable bit. So whether you want to receive it a single or how you're going to say it, but in the asynchronous mode, it's a don't care bit. So we don't have to be worrying about it. Then coming to the CREN, whether you want to receive the data continuously or not, you're going to say it with the help of CREN. So in the asynchronous mode, having it return with 1 enables continuous reception. Having it return with 0 disables continuous reception. Now tell me whether you want to receive continuously or not. Any data being transmitted you want to receive continuously or not? I have to receive. So CREN has to be returned with the value 1. By default it is 0. I have to write it with the value 1. So CREN is returned with the value 1. Okay. Next, ADDEN, it is the address detect enable bit. Okay. Now, if RX9 is returned with the value 1, okay, if RX9 is returned with the value 1, it conveys that you're going to receive the 9th bit. Okay, you're going to receive 9 bit. Okay, so only when we are receiving 9 bits, we have to be worrying about this. As of now, I'm receiving only 8 bits, so I can ignore this. Okay, but if you by chance are receiving the 9th bit, okay, so having it returned with the value 1 enables the address detection, enables the interrupt and load of the receive buffer when RSR is set. Okay, so when receive shift register is being set, it is going to detect where the 9th bit has been received. It is going to detect the address where the 9th bit will be received. As of now, I am not receiving 9 bits, so let me not worry about it. It is returned with the value 0, so let me retain it with 0 itself. Okay, there's a doubt. RX9 can be data or parity, right? How to tell whether data or parity it is used? So that depends on RX9 bit. This RX9 bit is not data or parity. It is telling whether you will receive 9 bits or 8 bits. So that is with the RX90 bit. So if you are receiving 9 bits, then RX90 bits will have a ninth bit of data. If you're receiving 8 bits, then RX90 will be used for parity. Okay. Now, F error is frame error. If RX9 is 1, then data has no, yes. So then you will not receive parity. RX90 is going to receive the ninth data bit instead of parity bit. So F error is framing error. Generally what happens is you're going to transmit one frame after the other. And while the frames are being transmitted, you leave some time in between. You give some timestamps in between. So if you don't give that timestamp, if you continuously keep flooding the data, if the transmitter continuously keeps flooding the data and the receiver is not able to receive the data, then it leads to a overrun error. Okay, so if the data is not able to receive one after the other, if the data keeps flooding, you're not able to receive it one after the other, it leads to a overrun error. Framing error is, see, at max, you should have one start bit, 8 data bits, one parity bit, and two stop bits. Now, if there is more than that, if there is more than the required number of bits, then it is going to cause a framing error. And that framing error will be represented by having one return in the FERR bit and having it return with the value 0 in the FERR represents there is no framing error caused as such. So you can identify the framing error and overrun error with the help of F error and OERR. Yes, they are read-only bits. So you are supposed to read and identify whether there is a framing error or a overrun error caused. Okay. So these are the two registers. One is the transmitting shift register. The other one is the transmitting status register. Any doubts in this? Okay. Now we are done with setting the registers of transmitter and receiver. After setting the registers of transmitter and receiver, the next thing I have to do is I have to make sure my device is agreeing to work with the baud rate of 9600. I have to tell the baud rate as 9600. Now to tell the baud rate as 9600, I have a special register, that is UART baud rate generator. Okay. Now this is a special register which is used to specify the baud rate. Now if the baud rate is 9600, I have to tell my microcontroller that you have to work with the baud rate of 9600. Okay. So for that I have to write a specific value to the SPBRG register. So there's a register called SPBRG register which will be returned with a specific value. Okay, so that is with the value X. That is the X I have to write. For a baud rate of 9600, SPBRG register has to be returned with some value. For that we have a formula. SPBRG is the register which is used to specify the baud rate. Now the formula to calculate is, for BRGH with 0 we have different formulas. For BRGH return with 1 I have a different formula. Now if you remember, we wrote BRGH with the value 1. So we have to make use of this formula. So I have to use this formula, find the value of X for the baud rate of 9600. Okay. So now if you rephrase this formula, 60, okay, this will 1 second. Let me rephrase it, and I have to calculate X here. So this baud rate will come here, and this will, I'm trying to find it for X. Okay, so this will go here. Then the 16 will also get multiplied here. So 16 like this. I'm sorry, 16 like this. And after I lost the 16, I have to go with minus 1. There is plus 1, so I'm going with minus 1. Okay, this whole thing should be done with minus 1. Okay, so X represents the SPBRG register's value. For a baud rate of 9600, I have to write some value to the SPBRG register. Now, if I substitute this, can you tell me what is the value of X for a baud rate of 9600? F oscillating frequency will be 20 megahertz. Okay, and baud rate will be 9600. Yes, so this baud rate will be 9600. Okay, multiplied by 16. This whole thing, 20 divided by 9600 multiplied by 16 minus 1. So can you tell me what is the value of X? 129.20. You can take only integer. 129. If I'm not wrong, you have to get 129. So that you can have it directly written if you want. Okay. Or you can write the formula like this. SPBRG is equal to F oscillating frequency divided by 16 multiplied by baud minus 1. So baud, you are receiving it into the unit UART function. 9600 is passed as an argument that gets received by baud here, and that gets substituted here in the calculation. F oscillating frequency, we have a macro taken, and the macro is representing 20 megahertz. So that 20 megahertz is being substituted here. So when I have to achieve a baud rate of 9600, SPBRG register has to be written with the value 129. You either can have it calculated with the formula here, or you can look at the table directly here. So you can see for an oscillating frequency of 20 megahertz and 9600 of the baud rate, SPBRG should be written with the value 129. So I have 129. You either can calculate it with the formula here, or you can directly write SPBRG with 129 looking at the table. So in that case, if you fix it to 129 directly, if you want some other baud rate to be changed, then again you have to look at the table and replace it here. So instead, you can directly substitute a formula, and when you pass the required baud rate as an argument here, the SPBRG value will be calculated and it will be loaded. So SPBRG in this case will be written with 129 for the baud rate of 9600. Okay. So in this case, when it comes to the baud rate speed of 1, okay, the least what you can achieve is 9.6 itself. Okay, so 9600 is the starting frequency what you can achieve when you are fixing baud rate speed, baud rate as a high speed. Okay, so that is the initializing function of the UART block. Any doubt in this? We can use higher value also. Yes, sir. So like if you want the data to be transmitted in a still faster rate, you can give a higher frequency also. You can use any of it in the table given here. So you can use 19.2, you can use 28.8, but you can see the rate of errors in these cases are comparatively higher. Like only from 9.6, the error rate is only 0.16. So according to that, you have to choose. And these are the only options available for 20 megahertz of oscillating frequency. Okay, understood the initializing function? Yes, 19.2 is also fine, but you have to check whether the host or whether the other device is also able to work with 19,200 as the baud rate. Okay, so I'll continue in 1 or 2 minutes. If you want, you can make a note of this. Okay, can we continue? Fine. The next thing is when it comes to this program, whenever I want to receive some data, I'm going to make use of a function called getChar. And if I have to transmit a data, I'm going to call a function called putChar. Okay. So when I have to receive some data, I call a getChar function. I have to transmit some data, I call the putChar function. So first and the foremost thing, we got to know how we are going to transmit the data. So let me also see how to receive the data. So here I wanted to add a few more things. Okay. So first, the UART transmitter. Okay, let me first discuss reception, then I'll come to the transmission. Okay, so universal asynchronous receiver. So remember, the actions will not happen on the transmitting or the receiving pin directly. So you are going to make use of certain uh, registers for it. So now, the heart of the receiver is the receive shift register. So remember the names of the register. It's receive shift register. Now, after sampling the stop bit, the received data in the RSR is transferred to the RC-REG register. If the transfer is complete, the flag bit RCIF will be set. Okay. Now, whenever you are going to receive the data. So let me say receive. So when you are receiving the data, first, bit by bit, data gets received at the RC7 pin of the microcontroller. Now, after receiving it bit by bit, the data gets received in the RSR register. The 8 bits of data along with the start and the stop bit gets received by the RSR register, which is receive shift register. Now, once the receive shift register receives a stop bit, this 8 bits of data gets returned. This RSR register is also of 8 bits only. It stores only 8 data bits inside it. Whatever other bits it receives, it is just for the confirmation and it ignores it. Okay. So, how start? First start bit gets received by the RSR. First start bit gets received by the RC7 bit. That will be received returned to the RSR register, but it will not store it. It will discard it. Then 8 data bits one after the other gets received by the RC7 bit, and that 8 bit gets stored in the RSR register. Then one more parity bit will be received, and once the parity bit is received, it detects the parity bit. So it is going to confirm with the parity of its calculation. Actually, what happens is once this RSR receives 8 bits of data, it calculates the parity and keeps it ready. Now, once it receives the parity also, it compares with the parity of what it has calculated. Now, if it is a match, it continues. If it is not a match, it will not give me the data. Like it is like a wrong data I have received. Okay, it may give me some garbage data. So RSR is just going to detect. It is not going to store it inside that. It's a shift register. It is not storing it. There will be a small buffer associated to it. So it is not going to store it. You can observe here. This is the RSR register. 8 bits only is the RSR register. So the start bit and the stop bit will be stored in some other location. Okay, some other memory will be utilized, but RSR is going to keep a track of the start bit and the stop bits also. Only 8 bits of data will be stored in the RSR register. Okay. Now, after 8 bits of data gets received by the RSR register, that 8 bits gets returned to the RCREG register. It's the buffer register. So RCREG register will have that 8 bits of data stored inside it. And once RSR is done writing that 8 bits of data to the RCREG register, it raises an interrupt. It is going to have RCIF set with the value 1. Okay. Once RCIF is set with the value 1, if I want to collect that data, I just have to read RCREG register. Are you able to follow this? So all of these are happening internally. First, from RC7 bit, data gets returned to the RSR register, then RCREG register. Then once data is returned to the RCREG register, RCIF will be set to 1. Once RCIF is set to 1, I can read from the RCREG register. Similarly, when I have to transmit the data, I'm sorry. So when I have to transmit the data, whatever data I have got to transmit, that data has to be returned to the buffer register. So whatever data I have to transmit, that has to be returned to the buffer register, that is TXREG. From TXREG, that data gets returned to the shift register, TSR register. Then once TSR register is returned with the whatever data I have written, then TXIF bit will be set to 1. Okay. So TXIF bit will be returned with 1. If TXIF is returned with 1, it is a confirmation for me that the data will get transmitted. Okay, so TXIF is a separate bit. It's a different bit. It's a TXIF bit. So if TXIF bit is returned with 1, then it is a confirmation for me that the data gets transmitted. Okay, so that is how we are going to achieve. So whatever procedure is there, this procedure of receiving and transmitting, so we are going to have the uh, functionality written in a separate function. So first I have to receive, I want to receive some data. So whenever I want to receive some data, you can observe, I call the getChar function. You can see here ch is equal to getChar. I'm going to receive that. Okay, it's a getChar function. Okay, when getChar function is called, control will go to the getChar function. So first, I will wait till RSIF falls down to 1. Okay, in the getChar function, I'm waiting till RSIF is returned with 1. Once RCIF is returned with 1, I come out of the while loop. I'm going to return the RCREG registered value. So I have to read, I have to get the RCREG registered value, and I'm going to store it inside a variable called CH. Are you able to follow this? So same procedure. So once all the data is returned, okay, once all the data is returned to the RXREG register, RCIF will be set to 1. So I just have to wait till RCIF is set to 1. Once RCIF is set to 1, I make it back to 0, and I'm going to return the value whatever is in the RCREG register. Now I want to transmit the data back. So I call the putchar function by passing ch as an argument. Now in the putchar function, whatever data I want to transmit, I have to write it to the TXREG register. Then it gets returned to the TSR register, and TXIF will be set to 1. So I'm just waiting till TXIF will be returned with 1. The moment TXIF is returned with 1, it's a confirmation for me that the data is being will get transmitted. So I'm having TXIF returned with the value 1. So once TXIF is returned with the value 1, I will make TXIF return back with the value 0. And if I want multiple characters to be transmitted, I call put s function, and as long as I reach the null character, I call the putchar function by passing each character at once. So let's say I want to transmit hello. So first H will be passed to the putchar function, then E will be passed, then L, L, O. So individual characters gets passed to the putS function. Are you able to follow this? Okay. Now let me build this project and show you the output. Some errors are there. Okay. So here I have to do something. Yes, it is good to check. Okay. As of now, I have only one bit of data, 1 byte of data to be transmitted. I'm not checking that. Init config. Some errors it is showing. Comment. Oh, okay, right. I have just written. Okay, build has been successful. So first I have to open Qt.com. I also have to open PixinLab board. And in Qt.com, first I have to make some basic settings. First I have to click on settings. Please make sure baud rate is 9600 and device is COM2. Okay, baud rate is 9600, device is COM2, and here I have to make configuration here as well. Serial port has to be COM1. This you have to check. Now, after you configure both, I'm going to load the hex file. So I'm going to say load hex, and under UART sources, UART sources, driver pooling, distribute, default, production, the hex file. Okay. Now I have to open this. Okay. So this is the input window and this is the output window. Let me do file and reload last again. You can see UART test code is displayed as an output because in my code, first in the initialization, I have called put as UART test code. Okay. So that is why you can see UART test code as an output. So put as, that means the put as function started transmitting character by character. From this microcontroller, it transmitted U, then A, then R, then T, space. So like this, it kept transmitting one after the other. It is received here. So whatever I transmit here as an input, first I'm transmitting character A from the QTCOM that gets collected by your microcontroller with the help of getChar function. Then putChar function transmits the same character back. You will see a here printed in the output. You can see character A I transmitted, A here you can see as an output. Character B I transmit, B is seen. So whatever I transmit, it will be seen here as an output. Are you able to get this? And this is how we are achieving UART communication protocol. Are you able to follow this? Okay. So QTCOM configuration. Okay. I'm showing it again. So sorry. I have to go to settings. So baud rate has to be 9600. Data bits has to be 8. Then device has to be COM2. So after making this, you have to click on open. And here you have to go to file, configure. The serial port has to be COM1. Saurabh, I didn't get not on PIXIM in the sense. Why COM2 and COM1? That's a pair of, like, it's the pair you are going to use in serial communication. Actually, when you go to tools and click on serial terminal, it directly will launch the QTCOM by itself. Now, if you go to the serial terminal, let's say contents I'm going, okay. So here I will go to PIXIM lab. Okay, here I'll show 1 second. Serial communication. When I go to serial communication, you can see for Windows, PIXIM lab port has to be COM1 and QTCOM has to be COM2. So that is how the establishing of the communication happens. So that is how the software has been designed. Yes, transmitting and receiving will be displayed on QTCOM only because it has a window to show that. But on our PIXIM lab, we don't have a window to show that. So that is why I cannot display that character, whatever I'm receiving or whatever I'm transmitting. If you want, you can have that displayed on the CLCD. Yes, that is possible. Okay, so always same COM1 and COM2. Yes, you have to use COM1 and COM2 itself most of the times. But generally, if that is not possible, when you are creating a virtual pair, you can create COM2, sorry, COM3, COM4, COM5, COM6 and all. So that depends on how you are doing the installation as well. Where we did both grounded. Actually, QtCom is an application which comes with the PiximLab board itself. So because it is a software which comes with the PiximLab itself, we don't have to externally show you the ground. Okay, but ground is happening internally. Internal common ground connection is being done. Okay. So next we have one more program, we have a program for interrupt. Do you want me to continue now, or we will do it in the next class? Because that will take around let's say 30 to 40 minutes it will take. We didn't use serial port application downloaded today. You use the same. Whatever you used QtCom, that's the serial port. Are you asking about TerraTerm? Okay, TerraTerm is something we will use in the next example. So there is a small drawback of QtCom for which we have to use TerraTerm. Okay. So one more program of polling, like one more program, we will see it with respect to the UART in the next class. Virtual serial ports, that is what I said COM1 and COM2. So they are virtual serial ports. So COM1 and COM2 are virtual serial. So input from laptops we are sending, and to convert parallel data from CPU to serial QtCom we are using. Input data, yes, we are sending from the laptop, and in order to achieve serial transmission, we need an application which works on a serial transmission, which is why we are using QtCom for that. Okay, fine. So the rest we will QtCom covered parallel to serial write. Yes, that converts parallel to serial. So instead of transmitting all data at once, you are transmitting it bit by bit. Okay, fine. So the rest we are going to see it in the next class. In hardware, where do we connect? In hardware, you don't have to connect serial port. There will be a cable provided to you. So there you are going to establish the communication. With the RS-232, you can establish the communication. Okay. Here is your QR. Please have your attendance marked, then quit the session. We'll continue the next example of UART in the next class. Thank you all.